last webinar. IEEE Consumer Product Society provided this year several webinars, and all webinars are available on the Consumer Product Society website. Today we have Dr. Anirban Sengupta. He will be talking today about the anti-piracy aware IP chipset design for consumer devices. Just let me introduce our speaker today. He holds a PhD in Maths of Science in Electrical and Computer Engineering from Horizon University, Toronto, Canada, and he's also registered as Professional Engineers of Ontario. Dr. Sengupta has many research in the IT and also in cybersecurity. He is also author of many papers and journal published in conferences and journals. Dr. Sengupta also is a distinguished speaker for the IEEE Consumer Society. Dr. Sengupta, the floor is yours.
Okay, thank you, Wahab. Thank you, everyone. So, good morning, good afternoon, and good evening at different parts of the world. I take the privilege in giving my talk on a very interesting topic, which is called anti-piracy aware IP chipset design for C devices. So, before I actually get into the technical content of the presentation, let me give you some highlight of the recent journal publications that we made in this area. What I would do basically is handpick some of the most important ones and give you more details about this. So when we talk of consumer electronics vulnerability, what we are basically looking at which stages of the design flow in the consumer electronic hardware design process an IP code could be vulnerable. Now, starting from the specification stage and then followed up with the third-party intellectual property vendor integration, followed with schematic and layout generation, and finally fabrication, every stage of the design process is somewhere or the other prone or vulnerable to external threats and susceptible to external attacks. So we have to ensure through proper mechanisms at every stage of the design process that we have formal mechanisms to protect or safeguard the system. Now, when I'm talking of the word threats to an IP code, let us have a look at what are the popular threats that the current industry faces, or what we are looking at one of the most important threats that can lead to billions of dollars of loss when we try to make a system on chip for a consumer electronic device. The most important one that I would like to highlight is called false claim of ownership, followed up with piracy, Trojan insertion, and ownership abuse. So these all four are very important in the context of C device. The mechanisms to counter or protect this are digital watermarking, computational forensic engineering, IP metering, logic or structural obfuscation, and few others. So what I would do today is focus on digital watermarking to show how an anti-piracy aware chipset could be made, and also would give you a detailed analysis of computational forensic engineering, as these two methods are widely I would say acknowledged and extremely popular in tackling this method. The way how we do it, I'm going to present that. In a typical IC design flow, it starts off with the algorithmic behavior of the DSP design, that is a very common component in the C device, which is used for performing high level synthesis, and the synthesized RTL design is further subsequently fed onto logic synthesis that generates the gate level netlist, followed by the physical design, physical verification, and fabrication. And finally, we end up in the packaging and testing phase, where you get a tangible form of the system on chip that is used for C device. So this is the proposed design flow for the anti-piracy aware IP chipset design for C device that is used for detecting IP piracy, cloning and false claim of ownership problems. The primary inputs for this approach is the application, that is the behavioral description of the DSP, the library and the resource constraints or configuration, which is used to perform scheduling followed up with hardware allocation and binding, and subsequently which is called register allocation to find out the optimized number of registers used in the design. Parallelly, we can start in selecting our desired signature that needs to be implanted onto the design, which needs to be decoded to convert into respective watermarking constraints, and then these constraints would be fed onto the register allocation design, where we finally get a modified register allocation information in the scheduling. This entire process is then converted to multiplexing scheme, which is used to find out the connectivity information in the data path and the controller, and these two together form the watermarked IP core at the register transfer level. Now, this design is certainly anti-piracy aware, as any sort of piracy or cloning or any other sort of false claim of ownership an attacker tries to make can easily be detected. And finally, this watermarked IP at the RTL can be RTL synthesized followed by gate level synthesis and then the layout synthesis, and this final form is called the watermarked IP chipset. So, let me give you an example. Let us imagine before a watermark is inserted or implanted onto a design, we have a DSP behavioral description in the form of data flow graph shown in the example, where the vertical red lines are indicating the storage variables of the register indicated by notations R, G, B and Y, indicating red, blue, green and yellow, and the nodes are indicating the operations or the operations allocated to respective functional units or resources indicated by M1, M2, M3, M4, A1, A2, A3. The equivalent colored interval graph of the graph on the left side is shown here, where each of these nodes are indicating the storage variables as given here. Now, this indicates the design before watermark. Now, what we can do, we can also convert this colored interval graph into a tabular form that indicates the storage variable allocation as per the registers in each control step, and then we also have our watermark, which is based on the selected desired signature of the vendor, which in this case I have taken as 7-digit signature, and this is the corresponding decoded meaning. I remember I was speaking about this in my last talk, so we can kind of take a cue from there and understand how this is decoded. I am not going to go into details on this today, because we have already learnt about this in the last lecture. Now, what this indicates basically is that there has to be an additional edge between two variables, which is V2, V3, V2, V5, V2, V4, V2, V6 and so on. These external edges indicate that these two variables cannot be allocated to the same storage register. That means they have to be having distinct assignments. Now, as you see, by default the table on the left automatically considers all of these additional edges except V2, V6, which is placed in the same common register. So, this has to be taken care of, because this does not follow the watermarking constraints as it has been decoded here. So, what we will do, we will try to modify the timing table as per our design flow, which I had spoken over here in this step. So, this is the modified table where you see that V6, which was earlier allocated to register blue, is now allocated to register yellow, and the storage variables V7 and V10 are now allocated to new register, which is blue. The corresponding colored interval graph is shown on the left, and the corresponding scheduling diagram is shown on the right, where you could see that V2 and V7 are now allocated to blue registers instead of yellow register earlier. The next step is now to convert this into a multiplexing scheme for registers, where we will speak about the register blue and register yellow. So, as you see, the table on the lower bottom half is indicating the blue register information, which contains the watermark. How we get this is from the graph we just now spoke here. So, if we look into the blue register has its input, first input coming from register I3, and the input goes into resource M3 in, and that is what is written here. Register I3 is the input and the output goes through M3 in. For second, which means the control step number 1, we have here where the input comes in from M4 in and the output goes to A3 in. So this is the M4 out and the input goes to A3 in. So similarly, we build the connectivity information of the blue register, which indicates the watermarked information, and this is the one which is without watermark, which is built upon based on the graph which we had before watermarking, this one. The same process has to be repeated for the next register yellow, because this has also got affected because of change in the storage variables. Please keep a note that register red and green do not change, only the register blue and yellow changes in this case. Now once we have made the necessary changes to incorporate the watermarking constraints onto the multiplexing scheme table, we can extract the multiplexer circuit information from here. The multiplexer structure, as is corresponding to the table given here, is shown on the right, where you could see register I3, M4 out and A3 in are coming from here, and M3 in, A3 in and M3 in are coming from the last column. Similarly, the multiplexer circuit for register Y is based on these 4 input variables, and the output is derived from the last column. Now once we have the multiplexer structure and information of the circuit available to us, easily put this into a final corresponding data path, where you could see the register blue and yellow are exact replica or what we have extracted or derived here, and the remaining ones are just indicating by following the same process how we can get the connectivity information of register RG and resources M1, M2, M3, M4 followed by A1, A2, A3, which are the resource informations of the scheduling graph. The primary inputs here are register I1, I2, I3 and I4 and clock and reset, and the final outputs are register Y1 and Y2, and this is finally what we get as a chipset. We have the supply voltage, ground and the primary inputs and outputs. So similar process can be adopted for any DSP application when we want to build a system on chip for consumer electronic device, which can be anti-piracy aware as it incorporates all the watermarking constraints onto that. Okay, so we are done with the first half of the presentation. Now let us move to the second half of the presentation, where we are going to focus on a new technology that we have proposed, which handles the anti-piracy aware problem by detecting the piracy, cloning and false claim of ownership. It is called computational forensic engineering. The generic design flow of CFE, in short, starts with feature and statistical data collection, followed by feature extraction, entity clustering and validation. So what is a CFE? So CFE problem can be understood as follows. Given a solution S to a problem P, having a finite set of algorithms AN applicable to problem P that can generate a solution S, the aim of CFE is automatically identify with a high degree of confidence that algorithm or tool I has been applied to generate solution S. What we now do is we will customize the generic flow on the left to make our own design flow, which is called IP core feature analysis, followed by performing IP core feature extraction, and finally performing the matching and validation of the IP core. The first step, which is the IP core feature analysis, further comprises of these 4 steps, which is studying the HLS tool of each competing IP vendor, followed by deciding the common design and parametric features, then creating the feature set, and finally creating the device extraction rules for each of these feature set. So let me get into the details. So what's the problem statement? That we have a set of competing claiming HLS tool vendors who wants to claim ownership of the IP core, and we have to find out who is the legal or genuine owner. So we are trying to resolve the piracy issue, and we are also trying to resolve the false claim of ownership issue. Each of these HLS tool vendors, starting from 1 to n, are capable to generate an HDL, which is hardware description language of the IP core that is used in the C device. We indicate that by a variable called IPVN. Note, The IP core whose owner is to be identified is termed as IP ID, and IPIS generates as output through nth competing HLS tool vendors, where each of this is known as IPVN. If there are n number of claimant parties who are claiming the ownership rights of IPID, that is the IP core providers are claiming that the IPID has been generated by the respective HLS tool. The goal of the CF is to find out who is the rightful owner in case of resolving piracy issue in a C device. So, as I just said, for each of these IP cores, we have the HDL tool, HDL vendors first available, which will be used to generate the corresponding HDL designs using the HLS tools, and then we also have the given IPID HDL whose identity or owner has to be identified. So, each of these HDLs along with the HDL of the given IPID is fed into the proposed automated computational forensic engineering method. What we do, we first identify the generic features of HLS and the RTL IP core design, and we identify the unique features of the HLS and RTL IP core, and then we start devising unique methodology for extracting the features for each of these IP cores. So, the feature set comprises of two different types of features. One is called the unique feature, second is called the generic feature. So, unique features in this case for HLS tool based IP cores are pipelining, chaining, multicycling, reliability, loop support, design objective, and Trojan security. In the context of the current designs that are used in C device, these unique features are extremely useful. However, there are also some other generic features that include scheduling algorithm, resource type, bus width support. So, what we will do that based on this, we will feed onto the IP core feature extraction, where we perform the feature extraction and store them onto a set called feature set, and finally that would be used to decide the matching process on who is the rightful vendor. Before we get into the feature extraction rules, let us note some very important points. When somebody wants to apply CFE for IP core protection, these important points have to be kept in mind. The first is, the HLS tool may employ stochastic algorithms that may have some control parameters such as seed population, terminating criteria, and may also target multiple technologies. So, each separate run of these HLS tool may slightly produce different IP core designs for the same application. So, selecting a technology or control parameter dependent feature set would require the environment of the tool to be reproduced exactly while verifying ownership through CFE. On the contrary, if we select the technology or control parameter independent feature sets, that does not require tool to be executed in the exactly same reproduced environment. So, definitely in terms of recommending what type of feature set has to be used, is always advisable to go for technology or control parameter independent ones, so that you do not have to reproduce the environment exactly how it was done. Further, the parameters are also based on internal algorithmic properties of the HLS tool, thus it allows verifying ownership accurately despite having slightly different IP core solutions. I will get back to this as and when necessary. Let me go on to the feature extraction for better understanding. Okay, so let us have a look at a comparative study of CFE versus Watermark. Now, in terms of the techniques, both try to have the same goal, that is to identify who the real legal owner of the IP core is. However, in case of IP watermarking, there is certain chances of hardware overhead resulting due to storage registers, which is absolutely nil in case of CFE. The degradation in quality of performance may also incur if not taken care of well while incurring or while inserting the watermarking constraints. However, there is absolutely zero chances of degradation in the quality of the design in case of CFE. In case of protection, both try to go for same, and in terms of complexity, they both are equally complex. In terms of the possibility of threat, there is a higher existence of threat because there is a reverse engineering step in case of IP watermarking, which does not exist in case of CFE. And in case of time complexity, certainly CFE is a bit slower compared to watermarking, because CFE involves multiple steps such as feature and statistical collection, extraction rules, and validation. Okay, so let's talk of the first feature. The first feature is called scheduling algorithm, and the process to extract or detect whether the scheduling algorithm is ASAP based, ALAP based or list based, because these three are the most popular. We have devised the following rules. For ASAP, all the functional units of the independent operations in the data flow graph must have been activated in the first control step, and all the dependent operations and its successors should be placed in consecutive control steps based on their dependency. In case of ALAP, it's just the opposite. All the FUs must have to be activated in the last control step, and all the parents and its predecessors have to be placed in consecutive control steps based on the dependency. If these two algorithms have not to be satisfied, then list comes into the picture, where for list to be satisfied, we have to have a contrary condition in the context of ASAP and ALAP. So list will devise A and B rules, which is just opposite to ASAP, and C and D rules, which is just opposite to ALAP. If any one of these conditions are detected, then we know that what is the scheduling algorithm used inside that design or IP core. The second feature is called resource configuration type. In this, what is done is typically we try to extract the information of what type of resource configuration is used. So possible that if two IP core vendors having common or different HLS tools are trying to generate an IP core, one may use an adder subtractor unit to generate the design, and other may use an adder and subtractor separately to generate the design. So we can detect the difference through this feature, which is the resource configuration type. Similarly, both the HLS tools may not be using the same bus width support. So it's important to have a note at what is the bus width, whether it's an 8-bit data or whether it's a 16-bit data or whether it's a 32-bit data, so on. So based on the data width, we can also find out what HLS tool may have been used to do that. The fourth feature is called MultiCycling. So what is basically done here is that in MultiCycling, typically we try to satisfy this condition if MultiCycling exists. So if the end time, so CACE FUI indicates the end control step of FUI. If that is greater than the start control step of FUI, then we know that there is a MultiCycling incorporated into the design. The next feature set is called chaining. What it is doing is basically there is a possibility that several small operations may be overlapping in time duration with a larger operation. So in this case, let's say the larger operation here is multiplier that takes 40 control steps, and adder usually takes 1 control step. So we have devised an algorithm to detect if the property or feature of chaining is existing in the design or not. So I will explain what that is. For loop I equals to 1 to n, and for j equals to 1 to n and j not equals to I, that is, we consider this as ith operation and this as jth operation. If start control step of FUI is less than the start control step of FUJ, less than or equals to, that means in this case the start control step is 1 of ith operation and the start control step of jth operation is also 1. So this part of the condition satisfies, and the end control step of FUI, which is this 40, should be greater or equal to the end control step of FUJ, which is this, which is 2. So this part of the condition is satisfying with this example, followed up with if the end control step of FUI minus the start control step of FUI, which is the total duration that we are talking about here, which is 40, if that is greater or equals to the individual time durations of the operations, which is the end control step of FUJ minus the start control step of FUJ first, followed up with the end control step of FUJ, which is the next, minus the start control step of FUJ second. So these two are coming up here. So if this entire duration is larger than these two, then chaining feature is detected in the IP core HDL. I can give you some more examples. So typically in a HDL file, I have taken a snap of our project and I have put it over here. So we have the portion of the controller, we have the entity portion which declares the primary input output in terms of the ports, and we have the architecture where different type of signals are being declared. As you could see that the signal multiplier enable 1, which has been declared in the entity portion of the VHDL, when it is 1, it indicates the start of the multiplication operation, and when it is 0, that is it is disabled, it indicates end of the multiplication operation. So what we are seeing is basically it starts at control step 1 and finishes at control step 40. So this is how we can get the information of the variables, which is CSS and CSE, when we use this algorithm to detect whether chaining is existing in the HDL file or not. So let us move on to the next feature set. It is called data pipelining. So what it does basically is we try to secure and satisfy this condition to check if data pipelining exists. So if the end control step of the first data set, this is the first data set, the same behavior is being repeated for the second data set, that is the concept behind data pipelining, that we try to do as much parallelism as possible so that we can have improvement in performance. So if this has been done in the design, this condition has to be satisfied. So we can check it. If the end control step of first data minus the start control step of the first data is greater, that means this part is currently 41 control steps, as you can see here, is greater than the end control step of data 2 minus the end control step of data 1, which means this part comes out to be 40. So 41 is greater than 40, so we see that this condition is true, and that means there is a data pipelining in the design. So we can check the same information in the HDL file. How? So for example, in case of control step 42, we have register Y indicating the output of data set 1, which is here, and again in control step 82 we have the output of data set 2, which is indicated by the output register Y again being activated as 1. So if we apply this condition and we see this part becomes 41 and this part becomes 40, as I just now explained. If we put CSE N1 as 42 and if we put CS N1 as 1, so this part is 41 and this part is 40. So this condition is satisfied. So by looking at the HDL of the IP code, we can also find out if there is a data pipelining feature. Let us move on to the next feature. It is called reliability. So in this feature, what is done, it checks the top level entity HDL code of the IP code for DMR concept. So DMR stands for dual modular redundancy, is usually done in order to make a design fault secured detectable. Okay, if we want to know whether there has been any transient fault or any other sort of fault occurring in a C device, to find out whether there is any property of automatic detection of that, usually DMR is made by the vendors. DMR designs are made by the design. So what it basically does, it checks for the following condition. If in the HDL code of the data path there is a port map condition which says output register signal 1 followed by output register signal 2 are the inputs, and it leads on to a comparator output signal, which is in this case this, then there is a DMR. If such a scenario is existing, then the reliability feature is detected. The next feature is called Trojan Security. What it does basically, it also checks for DMR, because in Trojans also is very mandatory to have two different copies of the same design being replicated. However, both have to be executed through two distinct vendors. So that's why I marked over here vendor V1 and vendor V2. So it checks for two possible conditions. So in case of reliability, it checks for only one condition, and in case of Trojan security, it checks for two conditions. So first part of the condition remains same as I explained in the last slide. However, it checks an additional condition, which is if the input module library contains design parameters corresponding to area, delay, power, etc. from two distinct vendors, then we know that certainly there must have been two vendors used, and two vendors are typically used when we incorporate the Trojan security in the HLS IP code designs. So through this mechanism, we can easily detect if Trojan security is present or not. Okay, so now we are pretty much done about the feature extraction rules for the 8 features which I have just now explained. Now let us look into the IP code validation process. So we have defined a formula or a metric which checks for total number of matching features divided by the total number of features existing in the feature set times 100. If both the numerator and the denominator matches, then we have a 100% match, and only if there is a 100% match, then only a particular claimant or a particular HLS tool vendor can be awarded the ownership of the IP core. So, I will give an example. As you could see, this is the IP ID, okay, where we have these features which I just now explained, starting from scheduling till ending till Trojan Security. So, what we do, we basically try to extract the features of the HDL of the IP ID, and this is what the information is. That is, this is list, this is adder multiplier, yes, there is a chaining, it is an 8-bit bus width support, there is a data pipelining, there is a multicycling, this is a design objective, there is no reliability, it is a DFG, and there is no Trojan security. And based on these competing tool vendors from ICT1 till IPCT7, these are the 7 claimant vendors who are trying to get ownership of it, but of course 6 of them are falsely claiming ownership and 1 of them is correct. We have to find out which one is it. So, we generate the HDL codes from each of the HLS tool vendors and apply CFE on that, and this is what we have got, the feature extraction of each of these tools. However, if you note, only the 7th HLS tool exactly matches with the IP ID, the one whose identity has to be determined. So, in that case, what we see that we typically have 100% match, whereas the remaining ones do not have 100% match. So, we can convincingly and confidently say that for the benchmark JPEG IDCT used in C device, this is the vendor who has actually made that IP core, and the remaining 6 are falsely claiming ownership. So, we can easily detect piracy. The same process has been done for the other benchmark, which is called DCT, that is often used in JPEG compression decompression process, discrete cosine transformation. And as you see, again for IP ID, the only tool or vendor that exactly matches with this is the 5th one, where we have a 100% match. So, this is the genuine or legal vendor who can be awarded the ownership. I have also tried to put a comparative study of the hardware features in terms of the storage variables used in watermarking, IP protection based methods and the proposed CFE based methods. As you can see, for all of these DSP applications that have been tested here, starting from filters to JPEG to fast Fourier transform, DCT, XY, whatever it is, you could see that in all of these individual benchmarks, the proposed CFE does not consume a single storage registers. So, therefore, the hardware overhead is completely 0 compared to watermarking. So, I have presented here the average feature extraction time in milliseconds for each of these features that I have just now explained. Certainly, as expected, the scheduling algorithm is certainly taking more time in extracting the feature compared to the other feature set, where loop support can easily be detected by reading the input library and input file to check if there is a loop condition available or not. If there is no loop condition, then certainly we can easily make out from that. So, these are some of my references that have been used today for explanation, and I will just briefly talk about that feature set information, which is very important, which I said I will speak about right at the end. So, I will go some slides back. Yeah, so these are some of the very important things to note when we want to talk about CFE and try to practically apply to HDL IP cores used in the industry. So, first of all, we just need the executable version of the HLS tools corresponding to the N claiming IP core vendors. This is analogous to having signature detection step in watermarking, where signatures from claiming vendors are taken as inputs to determine whose signature exactly matches with the given IP core. Procuring the RTL HDL of the IP core is also practical, because the given IP core can be obtained from any one of the claimants, as they all claim ownership of the IP core. Except the original vendor, all others have stolen or counterfeit copies, but we really do not know right at the beginning who the actual owner is. Also very important to note that the proposed approach does not require access to source codes or package information of the HLS tool of the N claiming IP vendors. We only need the executable version of the HLS tools, which is used for computing who the actual owner is. Thus, CFE approach does not require any secret in-house information or any information about the internal algorithms, which a vendor may not be ready to disclose. So, we are safe in terms of applying CFE for that. The executable version of the HLS tools would be run to generate the RTL description, which I have been referring to as HDL or VHDL, known as Very High Speed Integrated Circuit Hardware Description Language, which in turn will be used to extract the relevant feature information for analysis without accessing the tool source code at all. And finally, a genuine IP core vendor will always be willing to share information about the IP core, as he is a genuine vendor. So, we will always have a chance or a possibility of getting the RTL of the actual IP. So, these are some of the very important things that have to be taken into account when somebody applies, or a company or a research practitioner applies computational forensic engineering for IP core protection in C device. So, finally, I will close my talk today by giving you a glimpse of my publication details that we have got based on the projects that we have been doing in last few years. We recently had a paper in IEEE Transactions in Consumer Electronics on a similar topic, and I would be glad to answer if you have any questions. Thank you so much.
Thank you very much, Dr. Sengupta. It is very interesting talk, and I would like to express my appreciation for your interesting webinar on behalf of Consumer Free Society and its members, and for the time and effort that took you to share with us your thoughts and experience. I would like to ask our participants to write on the chat window any question you like, and Dr. Sengupta will be more than happy to answer. Otherwise, please, you can send it to, in case you don't have the time to type and you are short on the time here. But please, I mean, if you would like to get back to us, this is the is your your email address?
Sure, I have my email address right at the beginning of the slide.
Okay, perfect.
Just get back to that once. So yeah, as you can see, this is my email ID. So please feel free to ask me any questions on the topic that I have presented today. I will be glad to answer.
Excellent. So I posted also on the chat window.
Sure.
And people, they can send you an email or to my email also if they need more information. So I put the emails on the chat window, and we are looking forward to receive your emails or any questions that you have. Otherwise, once again, Dr. Sengupta, thank you, and thank you for all participants that they participated in this webinar. And I wish you all the best, and we'll see you next year with the same series of webinars from IEEE Consumer Finance Society. And I wish you all the best.
Thank you.
Happy holidays and happy New Year.
Thank you, Dr. Al-Muradi, and wish you all the same, and greatly appreciate your support and your time. Okay, thanks a lot. Have a nice day.
Thank
you.
You too. Bye-bye.